Is to open up your brand new packet, and on the back of the blue cover I'd like you to write the following definition. I'm telling you it's a definition, so that means we can treat it like a definition. Lines, rays, or segments that intersect at right angles are perpendicular. Please write down that definition. As you're writing the definition, think about how we're going to be able to integrate this into a proof, knowing that if we use a definition as a reason in a proof, that we will have to write it in if-then form. So how could we turn this definition into an if-then, a conditional statement? Yes, Marissa?
If lines, rays, or segments intersect at right angles, comma, then they are congruent.
Or rather...
Oh, then they are perpendicular.
Perfect. So let's write that down. If lines, rays, or segments intersect at right angles, then they are perpendicular. And that sign, the upside down T, is the shortcut sign for perpendicular. So you'll see that in problems it will say given segment this perpendicular to segment that. Hold on. All right, now that we've written the definition in if-then form, I'd like you to write the converse. Who can write the converse, keeping the subject in the hypothesis? Lucas.
You write the converse, keeping the subject. Okay.
So the subject would be lines, rays, and segments, right?
Yes.
So we have to keep that part in the
if,
hypothesis.
Okay. So if lines, rays, or segments are congruent, then they intersect at right angles.
I think he meant to say perpendicular, but otherwise that's fine. If lines, rays, or segments are perpendicular,
Yeah, perpendicular. That's what I meant. Sorry.
good, then they intersect.
Wait, is that how it usually goes when you write a converse, or just with this?
Converse is always just the flip-flop.
Yeah, but like keeping the subject. How does that work?
Well, it just depends on what type of statement it is. Sometimes there are two subjects, but we have, if we just said if they are perpendicular, then lines, rays, and segments intersect at right angles, it wouldn't make as much sense. So if lines, rays, or segs are perpendicular, then they intersect at right angles. And remember that we need to have both variations, because depending on the order of our proof, we have to have we have to be able to say sometimes our conclusion is right angles, sometimes we need our conclusion to be perpendicular depending on what we're trying to say. Now, looking into on page 3, so the first page of your packet, we can do an example that uses perpendicular. So given that AB is perpendicular to BD, and we know that if two line segments are perpendicular, then what? They intersect at right angles. So the logical jump we are reading from our givens is that angle ABD is a right angle. So we're going to go ahead and mark that on our diagram. We know that this angle, the whole thing, must be a right angle, and therefore it's 90 degrees. Notice too that this does say given, but it's not a proof, it's a find. We're trying to use the algebraic expressions over here to solve for x and then find CBD. So knowing that this whole angle is a right angle, who can write an equation that will help us solve for x? Jazzy.
Line AB, or is that wrong?
Well, we're not dealing with lines because the expressions are...
C, B.
Why don't you use the x's? Can you use the expressions?
X plus 2x minus 3
Good.
equals 90.
Perfect. That's exactly what you should do. We know that each angle has its own assigned expression, but the sum of those expressions must total 90 degrees. All right, so combine like terms and add 3 to each side. Question? Yes, Abby.
I'm just still confused. How did we know? Oh, never mind.
All right, I'm glad I could help.
I think I know what she's saying. Is she saying how would we like, Abby, are you asking how would we like to know that it was a right angle?
Yeah.
Yeah, that's what I want.
We know we got the definition earlier in our notes today that if things are perpendicular, that they intersect at right angles.
I didn't see.
So this is the symbol for perpendicular, the upside down triangle.
Yeah.
Good.
Sounds
The
good.
thank you, upside down T. Now divide out the 3, and we get 31 for x. But it doesn't want to know what x is, it wants to know the measure of CBD. So the problem gives us that the measure of CBD is equal to 2x minus 3. So we're going to plug in 31 for x. And double 31 to get 62. Minus 3 to get the measure of CBD is equal to 59 degrees. Yes, Griff?
Or can't we just do 90 minus 31?
We could, because this angle was equal to 31, because x was equal to 31. You could go 90 minus 31, and that would still give you 59. All right, let's move on, and let's use the new theorems today that we learned in a proof. So first things first, please write off the givens. PS, perpendicular to SR. And I'm just going to do it in one step. QR, perpendicular to SR. You should also mark those given facts on your diagram. And you know that if segments are perpendicular, then they intersect at right angles. So watch what I can do. I could put this little box here. That PS is perpendicular to SR, and that QR is perpendicular to SR. Now, look back at the theorems we have today. We have a theorem that says if perpendicular, then right angles. So what can we conclude from the fact that we have, for example, PS is perpendicular to SR? Lucas?
Well, we know that like if so they're perpendicular
Mm-hmm.
and they're both right angles, and all right angles have a measure of 90 degrees.
Mm-hmm.
And then if an angle has the same, if two angles have the same measures, then they're
That is a valid path to take, and we're going to do something very close to that. But what was the first leap that you made?
first leap that
From perpendicular to what?
perpendicular to
If segments are perpendicular, or if
if
then
segments that intersect at right angles, then they're perpendicular.
the other way around with the
If
converse.
segments are perpendicular, then they intersect at right angles.
There you go. So that means what? Can you name a right angle in the diagram?
Name a right angle diagram. Yeah.
Which angle?
Angle S.
Well, we can't just
PSR.
call it angle S,
PSR.
right?
PSR.
PSR. So we could say the angle PSR is a right angle. Now, can we name another right angle in the diagram? Andrew?
Angle QRS.
Perfect. Angle QRS is a right angle.
Is number 1 given?
Ah, yes, thank you. Our reason for number 1 was given. And we need to now write our reason for step 2. Marissa?
If two lines intersect, then
All right, so how about say if two segments are perpendicular. So if segs are perpendicular, then what was your conclusion, Marissa?
then 90 degrees.
Then they intersect at right angles. Yes, you can just read what we wrote before. So here, if lines, rays, or segs, we'll just use segs, are perpendicular, then they intersect at right angles. So we can transpose and write exactly that. If segs are perpendicular, then they intersect at right angles. Now, in chapter 1, we learned a theorem about right angles. If two angles are right angles, then they are congruent. And that's where we're trying to end up at. So, we don't actually have to go through and say that they're 90 degrees. We can eliminate that step and just say that these two angles must be congruent because they're both right angles. So angle PSR is congruent to angle QRS, and it's if two angles are right angles, then they are congruent. So the path that we took on this problem was that we made a leap from perpendicular to right angles to congruent. And that's the path that we have to take whenever we're trying to go from perpendicular to congruent. You can't skip the right angle step. Any questions so far? All right. I think that is all I have for you today. Good work.